Okay, let's dive right into this. Welcome to today's Explainer, where we're unpacking a truly fascinating development in the world of medical AI. We are looking at a recent research paper that introduces a system called SAGEAgent. It's essentially a self-evolving AI, and it's designed to fundamentally change how we approach clinical diagnostics for cancer patients. If you've ever wondered how artificial intelligence can be used to not just analyze medical data, but actually decide what data is worth gathering in the first place, well, you are in the exact right place. We're going to break down exactly how this complex AI framework operates, step by step. To really understand why this matters, we have to start with a very human question. Does every cancer patient truly need a highly invasive brain biopsy to accurately predict their survival? Because in clinical oncology today, the diagnostic process is essentially an escalating ladder. Doctors start with basic information and progressively move toward much more invasive, time-consuming, and frankly, expensive procedures. And the human stakes here are incredibly high. Every unnecessary surgery means unnecessary patient suffering, risk, and financial cost. But how do doctors know when it's actually safe to stop testing?
So here's our roadmap for today. We'll quickly run through the diagnostic dilemma, then enter SAGEAgent, look inside its brain, see some real-world decisions, look at the results and impact, and finally wrap up with a summary and some key takeaways.
Let's start with Section 1, the diagnostic dilemma and sequencing patient data.
To really grasp this dilemma, we first need to understand that in reality, medical data isn't just handed to a doctor all at once in a neat little folder. It's gathered sequentially. Think of it kind of like a detective solving a crime. If the detective looks at the security camera footage and can clearly, unmistakably identify the suspect right then and there, they don't need to block off the street and spend days dusting the entire city for fingerprints, right? The case is effectively solved early. Medicine works the exact same way. If early, simple tests give us a highly confident answer about a patient's prognosis, gathering every single possible piece of advanced medical data isn't just redundant, it's actively harmful to the patient.
The researchers mapped out this specific clinical order for glioma, which is a type of brain cancer, and they assigned a burden score to each step based on cost, time, and invasiveness. Step 1 is demographics, things like age and gender, super easy, so it has a tiny burden of 0.03. Step 2 is radiology, like an MRI. That's a bit more expensive and time-consuming, bringing the burden up to 0.14. But look at Step 3, pathology. This requires a surgical brain biopsy. The clinical burden literally skyrockets to 0.53. It requires an operating room, recovery time, and real physical trauma. Step 4 is genomics, analyzing the tissue with a burden of 0.30. To put that into perspective, the leap from an MRI to a biopsy is absolutely massive. So how does current AI handle this? Well, terribly, to be honest. On one side, we have static fusion models. These are incredibly data-hungry. They demand 100% of the data to give an accurate prediction, meaning every single patient is forced to undergo the full, invasive surgical workup. On the other side, we have reinforcement learning, or RL models. Now, these can decide to stop early, but they act as a complete black box. They just spit out a stop command with zero explanation. Naturally, doctors do not trust an unexplainable AI when a patient's life is literally on the line. So the crucial point here is that we need an AI that can stop early to save the patient from unnecessary surgery, but can also explicitly explain why it's stopping, so doctors can actually trust it.
Which brings us to Section 2, Enter SAGEAgent, an AI guided by experience.
Let's look at how the researchers designed SAGEAgent to fix these fatal flaws. Notice how SAGEAgent explicitly respects the strict clinical acquisition order. It doesn't just look at all the tests independently, it follows the real-world sequence. At each stage, say after demographics or after radiology, it pauses. It opens a decision panel, calculates the uncertainty of its current prediction, looks at learned rules, checks similar past cases, and actively asks itself, is the benefit of acquiring the next modality actually worth the clinical cost? For patient A, it decides the answer is no and stops early. For patient B, it proceeds. And most importantly, it does this using text-based reasoning that a human doctor can actually read and verify.
Moving on to Section 3, let's look inside SAGEAgent's brain to see exactly how it thinks.
To understand how it makes those distinct choices, we really need to look at its 3 memory pillars. The researchers built this system around a frozen large language model, an LLM, and gave it 3 distinct components to help it reason. First, clinical tools. These act as the agent's eyes. They take raw numerical risk and uncertainty scores from a medical model and translate them into natural text, like uncertainty is low. Second, episodic memory. This is the agent's memory of specific past patients. It searches a database to find patients with similar early test results just to see what happened to them. And third, semantic memory. This is the agent's internal textbook. It contains high-level, reusable rules that the AI has discovered over time through trial and error.
And this brilliantly illustrates how all of those pieces come together. Look at the flow on the left. The patient data enters the system. The clinical tools, episodic memory, and semantic memory all feed their text-based signals directly into the frozen LLM. The LLM then performs what we call chain of thought reasoning. It literally writes out its logic. It says, okay, step 1, I see rule 1 says to stop when uncertainty drops after an MRI. Step 2, all 3 similar past patients successfully stopped here. Step 3, weighing the benefit versus the massive 0.53 burden of pathology, I choose to predict now. And what's truly amazing is the loop at the bottom, self-evolution. Based on whether its decision was good or bad, it updates its own rulebook for the very next time, completely without human intervention or complicated gradient updates.
Section 4. Real-world decisions. Let's look at the path of 2 distinct patients.
It's one thing to see a flowchart, but let's see how this chain of thought reasoning handles 2 completely different humans walking into a clinic. We have patient A and patient B. For patient A, the MRI comes back with very clear markers. SAGEAgent's clinical tools report high confidence. Its episodic memory finds similar cases that didn't need any further testing. So, SAGEAgent safely stops early, entirely sparing patient A from a surgical brain biopsy. Now, patient B. Their MRI is a bit ambiguous. SAGEAgent notes the high uncertainty. The semantic memory rules dictate that when uncertainty remains high and the risk error is large, the agent absolutely must acquire the next modality. So for patient B, SAGEAgent recommends the full invasive workup. It's a completely personalized approach driven by logical, transparent reasoning.
Section 5. The results and impact. Doing more with less. The methodology is incredibly elegant, sure, but in the realm of medical AI, the only thing that actually matters is how it performs on real patient data. The researchers tested SAGEAgent on a massive cohort of 962 glioma patients, and this is the headline number: 55%. SAGEAgent reduced the average clinical acquisition burden across the entire patient cohort by 55%. That means, on average, they cut the required cost, time, and physical invasiveness of diagnosing these patients by more than half. Think about the incredible strain that relieves on the healthcare system and, much more importantly, the physical relief for the patients who just get to skip a brain biopsy.
But you might be wondering, did they sacrifice accuracy to achieve that? Let's look at the numbers. Here, the C-index is our measure of accuracy in survival prediction. The static fusion method, which is the gold standard that uses 100% of the data, hits an accuracy of 0.812, but it has a massive clinical burden of 1.0. The reinforcement learning method slashes the burden to 0.124, saving 88% of the cost, but look at the accuracy. It plummets to 0.729. It's cutting corners and discarding vital data. But SAGEAgent? It achieves an accuracy of 0.813. That's actually a tiny fraction better than the static model, all while safely reducing the burden to 0.451.
Now, what's really interesting here is visually seeing that sweet spot. Notice how stark the contrast is. You can see the solid gray bars representing high accuracy, anything above 0.8. SAGEAgent, highlighted in red, is standing right there with the top performers in terms of accuracy. But look at the striped bars representing the clinical burden. Every other highly accurate method requires a 1.0 burden, a complete invasive workup. SAGEAgent is the only method sitting in that perfect sweet spot, maintaining elite accuracy while dropping that striped burden bar by 55%. It's doing exactly what it was designed to do.
And finally, Section 6, our summary and key takeaways.
We've covered a lot of ground today, from the flaws of current AI to the self-evolving memory of SAGEAgent. So here is what you really need to take away. First, SAGEAgent successfully solves the sequential multimodal survival prediction problem by actually respecting the real-world clinical order of tests. Second, it replaces black box AI with fully auditable, text-based reasoning that doctors can verify themselves. Third, its self-evolving memory operates completely training-free, meaning it doesn't require complex, expensive neural network updates just to learn new rules. However, to be fair, the researchers do impartially note a limitation. The AI found it much easier to learn when to stop testing than when to continue acquiring data, which naturally requires a bit more exploration. And moving forward, this framework will absolutely require larger, multi-site clinical trials before it hits real-world hospitals.
I want to end on a quote directly from the researcher's conclusion because it perfectly grounds all of this high-level AI theory back into reality. The agent learns to skip invasive pathology for half of the cohort, suggesting that a substantial fraction of glioma patients may not require biopsy for reliable prognostication. Half of the cohort. That is hundreds of patients saved from an invasive surgical procedure without losing any diagnostic accuracy. That is the true power of cost-aware AI.
Which leaves us with one final thought. We've seen how SAGEAgent uses its clinical tools, past memories, and learned rules to weigh the very real human cost of a procedure. So if you were in the clinic and an AI could confidently save you from an unnecessary painful surgery by plainly reasoning through your medical data on a screen, would you trust its decision to stop early? It's a question healthcare is going to have to answer very soon. Thanks for joining me for this explainer, and keep questioning the data.